we have this before lunch part, which is intended to be introductory. So Paweł did some introduction on embeddings. He talked a lot about walks. So we thought of continuing this discussion about walks. So for example, if we have this walk on graphs with those node to vec and so on, so which nodes actually do we hit most often then? But my tutorial is, my tutorial is probably not to teach you graphs because most of you are experts here, but to continue what we discussed yesterday about Julia, so how Julia could be useful when doing graph research. So when I was thinking, okay, if we want to use Julia and we want to say something more about those walks that Paweł mentioned, then I thought that let's try analyzing with Julia. If you actually run a walk on a graph, what do you get? And my objective is the following. So I want to investigate if you run a random walk on a graph, which nodes you are going to visit, with what probability, or what is the average degree of the node you are going to visit. The starting point is that let's assume that we don't know anything about walks, so we are just, data scientists who knows this node to vec or whatever and knows there are walks, so wants to understand this a bit. So what does data scientists do? Well, data scientist says it's easiest to run a simulation and let's see what happens. And this is what I will do first. Then I will try to check, okay, what we learned from simulation. Can we really understand it using numerical computation? So still using a computer, but not simulating it, but analyzing the problem numerically. And finally, maybe when we get enough insights from numerical analysis, maybe we can actually prove something. So kind of we start from simulation, go through numeric model and finish with analytical solution. And we will learn, or probably you know that actually this is not a uniform walk. So, not all nodes are visited with the same probability. So the second part, I will say, but what if we wanted a walk that actually visits each node with the same probability in the long run? And I will do the other way around. So first I will say, okay, what could be the analytical idea that would allow us to get such a walk? Then I will verify it numerically. And finally, I will run a simulation to check if our analytical idea verified numerically actually works with simulation. So by this, my aim is two things. First is maybe, this going back and there again, like in Hobbit. So we go there from simulation to analysis, and then from analysis to simulation, maybe you would find it useful. I will try to justify how I believe it's nice to use, computer assisted work in mathematics to get some more insight or some ideas. This is what I.
In one direction, I understand why you want to do it, but the second direction, for the purpose, you know the answer, you just want to test your coding skills, or?
No, because sometimes you actually need to run something more complex on this graph than just to know.
I'm just teasing you.
No, so, you might want to do some embedding, for example. But of course, you can do it with pen and paper, but you just told us that you didn't do this, but you ran this. So this is the idea. So I want to go both ways, and those ways are chosen this way because I believe it's easier to first run a simulation to understand what is the distribution of the random walk if I pick every node uniformly. But actually, I believe that it's easier to analytically understand how you need to correct this walk to get a uniform distribution over nodes. And this gives you the idea how to write the simulation that actually also achieves this. And this is like the story. The second part is that everything that Przemysław showed you yesterday about, for example, sparse matrices, etc., we will use all this today.
Valid reason why you should do it, like MCMC, right? Method. You actually run the code to get uniform distribution on a very large state space.
Yeah. So maybe we will rediscover MCMC somehow during this talk, but we will see. So, but my point is that I'm not assuming that we know a lot. So, this is something that I typically teach my students. First, let me load the required packages. So this is fast. And what data are we going to use? So we are going to use GitHub Social Network dataset. This is a standard dataset of the GitHub developers. Essentially, you can think of that two developers are connected if they work on a similar thing. And we will want to work with this graph. Why I have chosen it because it is moderately large, so it has around 30,000 nodes, so it's not karate, which would be not interesting. It's large enough that you can say, okay, it could be a challenge to work with it, but at the same time, you know, I can fit with doing it in 1 hour. Because if I took 1 million nodes, then probably it would be much more expensive. So first thing we do, we read in edges of this graph. So we can, here we have ID1, ID2 is information about edges of this graph. And let me describe this data set. So what do I learn? That minimum edge number is 0, maximum edge number is 37,699. So I have 37,700 people in our graph. And we note that the original graph was probably created with Python because it uses zero-based indexing. So we will need to fix it. I tried, but if I zoom in, okay, it's better now because it didn't want to widen. Okay. So first we repeat the thing that Przemysław showed you yesterday. So maybe one thing, okay, what we see is that we have around 300,000 edges in this graph. And why is it relevant? Because, okay, first I create an empty graph, and then I add those 300,000 edges to it. So you see that so the time to do it was like relatively fast. And it was this question, can we use loops in Julia? Yes, we can. Because 3,000 times to run this loop was like almost instant. So I checked that indeed now I have all those edges put into the graph structure. And one important thing about walks, so Remco yesterday told us he only likes to work with giant components. So let me check if this graph indeed has a single giant component. I can use a connected components function. Again, almost instant, well, because it's an easy thing to check that indeed I have one giant component in the graph. This is relevant for walks because it means that I can reach everyone when it doesn't matter where I start. Eventually, I can visit every node. So before we start, let's have a look at degrees of this graph. So with degree function, I get a list of degrees. I can describe it, and I see that mean degree, and please remember it, mean degree is around 15, maximum degree is 10,000, again, Remco style, like we have this very heavy, very heavy nodes. And again, this will matter at some point. So it actually matters that for walks, that in typical graphs, some nodes are very heavy, because it will affect us how the walk evolves. We can look at a histogram, so without changing anything. I don't know why it's not showing, but in general, it's very skewed. Even after taking logarithm, like we have almost all nodes of low degree, and and we have a very long tail. And after log, we have this dot, as you remember, to vectorize the function. So again, this is just to verify that indeed our graph has have some nodes that have very high degree. Most of the nodes are of the low degree. So let us first start with the walk. So we have two questions. What is the average degree of the node that we visit? And with what probability we visit some other nodes in the long run. So when I typically show this, I ask, okay, we saw that average node degree is 15 in our graph. What do you think? What will be average degree of the node that we visit? Like in what range it could be? Can anyone guess? I know. So you don't have to guess, right? Yeah, we expect it to be large, and I will try to at least justify why it's large. But again, this is a tutorial introduction to Julia. So again, let's see how you can encode it in Julia. So we create a function I call travel. GH is our graph, I is where we start, and steps is for how many steps I want to run this walk. So then I will create dex is our, there will be the vector keeping degrees of nodes that I visit. So I start with just degree of node I. And visits, I will count how many times I have visited a given node. Initially, everything is filled with 0, so I visited node 0 times, except node I, which I just visited, so it's 1. And then, again, answer to the question, yes, you can use for loops. So I just run number of steps, pick a random neighbor, and then push, so append to the end of the vector the degree of the vector I just visit, and for this new location I add 1 to the visit. And finally, what I will do, I will return this vector of degrees and vector of visits. So what is relevant here again is that this is a pretty, I would argue, readable code, and I will just to show you that it should run relatively fast. So I run it for 10 million steps, just to have something that is, I don't know what's going on, because something must be going on with, if I'm streaming it, that it's cutting off the output. Okay, so I will have to stop running things. Sorry for this. So it took between 1 and 2 seconds to run those 10 million iterations. But if we take the mean of degrees of this walk, we don't get 15. We get something around 141. So much bigger value, as expected. Now, again, just to remind us, if we take a mean of degrees, this is 15.
What happens if you take the mean
I don't want to do this. No. Why? Why? Because I want to say the same in a different way. I want to say the thing in a different way. I want to say that I calculate this mean, but as a weighted mean, where weights are proportional to node degree. Is it okay? yeah. But you know, I agree with this is the same, of course. But why I prefer to say it like this? Because if I notice that actually calculated the mean of degrees with weights proportional to the degree gives me the idea, and this is this point where I say simulation might give you some idea, because if you say take a square, but why not cube? Yeah, but if I see that it actually works as taking a weighted mean, maybe it means that actually I am visiting those nodes with probabilities proportional to their degree, which we can check because I have this second vector visits vector, so I know how many times I have visited a single vector. So I could check whether those degrees and visits actually describe the same thing. So one thing I can do, I can compute correlation of those two things, which is almost 1. The thing is that it's almost 1, and this is the weak point of simulation, because I should get 1 in theory, but it's simulation, so it's almost 1. But it's only correlation, so I know it's a linear relationship, but maybe it's not going through 0, point. So let's calculate the linear regression, and I could do it in several different ways, but I chose this way for MATLAB users. So, you know, this backslash operation, which actually estimates me based on matrices. I don't want to go into the details of the notation, but based on matrices, I can just calculate the OLS estimate, where indeed I can see that it's 1 and 1 for the slope and almost 0 for the intercept, which means actually this is those degrees and visits do not only correlate well, but this is actually a linear relationship. So we have learned two things, that indeed this mean is much larger, but also like we got an intuition that probably the probability of visiting a node is proportional to its degree. Maybe not super surprising, but this is what we have learned. But we can then ask, okay, can I analyze it numerically with Julia? So first, let's create an adjacency matrix of this graph. So I get adjacency matrix, and as it was discussed yesterday, Julia by default will make this matrix sparse, because if it were not sparse, it would not fit into my memory. Because that's why I said earlier that I took large graph, not super large, but large enough that it could be challenging if it's not done properly. But by default, I get a sparse matrix. We see that we have around 600,000 non-zero entries, and it's 2 times number of edges, because I have because it's a graph, so it's symmetric. So I have this sparse adjacency matrix.
By the way, I'm curious, if Julia stores only the triangular part?
It could.
It could.
No, here it doesn't. No, here it doesn't, but I have a triangular, I have a matrix type that is aware of being symmetric, and then it's...
So it can be...
Yeah, but... Yes, so if I wanted to be more fancy, there is a type in Julia that is symmetric matrix, and then it would only store upper triangular part to not waste memory. And there is such... So it's not that it's possible, there is such type, but here the structure is simply for general also D-graphs, so it doesn't assume this. Sorry?
Operations could be slower.
Or faster. But The reason why I need normal matrix, not this upper triangular matrix only, because now I will want to use this adjacency matrix to encode my walk. And when I encode my walk, this matrix will become non-symmetric in a minute. Why? Because adjacency matrix tells me who is connected to whom. But then what is important that for each node, I can take its degree. And I know that, for example, for node of degree 1, I have 100 probability to go to a given node because I have only one way to go. If my node, for example, second node has degree 8, so I have 1/8 probability to go to a given node. So how do I encode those probabilities in a matrix? Well, I have those travel probabilities per unit. And now if I multiply my adjacency matrix by this vector, I get a transition matrix. And this transition matrix is not symmetric anymore.
But of course you could just do it separately.
Yeah. But then what is important, and this is something that Przemysław mentioned to you yesterday, if I do this multiplication, Julia understands that this is a sparse matrix still, so this transition matrix is still sparse, which means that it will be not using much memory. Because Julia understands that if I multiply sparse matrix by a vector, it keeps sparsity. So I have this sparse transition matrix. So what is a transition matrix? Transition matrix is a matrix whose row tells me with what probabilities do I move to from one point to another point, and this probability is uniform over all nodes. And the fact that it's uniform will lead to the fact that higher degree nodes will be visited more often. So now let us do the same what we did with simulation, but with numerical computation. So how to do the same we did with simulation, but with numerical computation? Let's say the following. Okay, I start with in every point with the same probability. I could actually pick any starting point because we know we have a connected one giant component, but let's just say that we start with something uniform, and then I say, okay, so how this distribution will change after one step? Well, I need to multiply my row vector by the transition matrix, and I will get the distribution after one step. And what I do numerically, well, I will do it like 100 times, and we will see where we get after we repeat this process many times. So now we have switched from simulation to numerical computation, so now there is no randomness. And again, by accident, we have discovered power method. Yes, because sorry.
Too late to be published.
Yeah, too late to be published, but in the end, this is the power iteration method. So Google made a business on this. So I can ask, okay, how can I get stationarity probability distribution? Okay. I destroyed it, but in general, I can compute it. And again, I did 100 iterations, but it was sparse, so it's almost instant still to compute it. And I can compare this stationarity probability to just, degrees divided by sum of degrees, because this would be theoretical distribution. We have hypothesized, and if we subtract them, we see that this is below numerical precision. So my numerical method also confirms.
Maybe you've done this, or maybe we can just do it now. Can you compute the two largest eigenvalues of the transition matrix? Would it be immediate?
Yeah, I know. That's why I say I rediscovered. So second largest would not be, because I'm recovering the first largest eigenvector, right? For the eigenvalue equal to 1. Yeah, okay, but so I could do it with eigenfunction, but for some reason, again, I don't know why my notebook doesn't play with Zoom and my output doesn't show, so I couldn't show it to you.
But did you compute it? I can the top eigenvalue?
No, I have not computed. So I have not computed it. No, I can do it during lunch break, but sorry, for some reason the output doesn't show. But anyway, we can see that after 100 iterations, the convergence is below standard assumptions of numerical precision. So
the graph is probably good
yes, but we will go back to this in a second. But just for those of you who have never seen this, let us try to convince us that indeed what we have just found is true, not only in simulation and numerically, but in general. So if we start with adjacency matrix where Aij is 1 if there is an edge between I and j, and 0 if it's not. So this is the matrix we had. Then I create this transition matrix by dividing Aij by di. Now what I have is that if I sum all those elements, the sum is 1. And what I will show that actually that D is eigenvector for the eigenvalue equal to 1 for this matrix. And this is pretty straightforward computation, which shows us that this is the case because Tij is Aij divided by di, and if I multiply one by the other, it's just the sum of d because Aij is symmetric. So indeed, here we verified analytically that our hypothesis is true. But what I find interesting is that gives me the idea how to correct this walk if I wanted a uniform distribution of this walk. So this walk does not have uniform distribution over nodes, but I could ask, okay, what if I wanted a uniform distribution? And why I think it gives us the idea, because when looking at this derivation from analytical perspective, there is one observation. What if my matrix T, because matrix T was not symmetric as we discussed, but what if it were symmetric? Could I make it symmetric? Why I would like, it would make sense to have it symmetric, because if it were symmetric, then for symmetric matrix S is equal to S transposed, which means that one vector of ones would be an eigenvalue of this matrix, eigenvector for eigenvalue 1. So if my matrix S were a transition matrix that were symmetric, I would, sorry? Yeah, then my walk would be uniform. So the question is, can we find a way to make it symmetric? And I can say the following. Okay, if I have a case that actually, so if I'm symmetric, I don't have to do anything. But if I have two entries that are not symmetric, so one is larger than the other, it's easy to make it symmetric. So subtract the difference from the larger one, but then you are left with some leftover. So where to put this leftover, not to break things? Well, put it on a diagonal. Because if you put it on a diagonal, you can add to a diagonal whatever you want. It still will be symmetric. So the idea is how to make it symmetric. Well, from the if you have two things that are should be symmetric, if one is in excess, move the excess value to the diagonal. So you say okay, then set those values to be equal and increase the diagonal by the difference. And if you change your definition of your walk this way, you get a symmetric matrix. If you get a symmetric matrix, this walk will be uniform. With uniform probability, we'll visit every node. So we should ask ourselves, okay, maybe in theory it works, but will it always work? And the answer is yes, because all those values here are non-negative. Moreover, another question could be, it's the only way to do it? And the answer is no. I could do it in other ways because I could subtract more, as long as I would get the same values on asymmetric positions, because I could subtract more and put more to a diagonal. But actually, we could say kind of this subtraction is of this family of subtractions best. Why? Because I put least value on the diagonal, which gives me still a symmetric matrix, which means that I have the least mass in the diagonal, and I don't want to be on a diagonal because diagonal is self-loop, which means I'm going back to myself, which is not very interesting. So out of many ways I could make this matrix symmetric, this is actually quite interesting because it's less degenerate, we could say, least degenerate. Okay, so here we see that it must work from theoretical perspective, but maybe I made a mistake in calculations. I often do. Pavel and Francois correct me. Unfortunately. So let's check if it works. So first thing is, let us do it numerically. So again, we are going back. So we did analytics, then numerics, because numerics was in the middle. So let's create our corrected walk matrix numerically. So I take the original transition matrix, and now I will work with a corrected matrix. But what is, again, from the perspective of computing interesting, that Julia exposes me an efficient way to find only non-zero entries in this matrix, and I do not iterate zero entries at all. And because the matrix is sparse, this will be quite fast. Not super fast, but quite fast. So I only correct things that indeed need correcting. And I will not run it, but it runs in around 10 seconds to create this matrix. So I'm iterating only non-zero entries. Now, as you can see, we have more entries in this matrix non-zero. Why? Because originally diagonal was 0, and now we have put something to a diagonal. But now we check if indeed the matrix is doubly stochastic, so summing over rows, and so dims1 means we sum in one dimension, dims2 in other dimension. Both ways we are okay. Actually, as we promised, this matrix is symmetric. And we check with our power iteration method that what is the stationary distribution, and indeed we see that with extrema that minimum and maximum are almost the same up to numerical precision. So indeed this matrix worked numerically. But now the last step is, okay, I have a nice theory, nice numeric solution, but can I efficiently encode it in simulation? So if I actually needed to simulate it, because as you have said earlier, I might have some more complex process I want to study that is not just multiplying two matrices, can I easily encode it? So I want to fall back to simulation, and maybe not astonishingly, because those formulas are simple, I can rewrite this condition that I move something to the diagonal with an easy condition for simulation. Why? Because I see the following. If I want to, I already sampled from where to where I want to move. I want to move from node I to node J. If degree of I is greater than degree of J, I don't need to do nothing, because we know that we haven't changed this weight at all. But if I want to move from a node that has a lower degree to a node that has a higher degree, well, I am reluctant to do it. And it makes sense from what we did initially. Why? Because we saw that with normal walk, we visit heavy nodes too often. So when I'm in a light node and someone tells me go to a heavy node, I say no. With some probability, I want to stay. And because probability of picking j was 1 over di, and I want it to be 1 over dj, where I need to correct with di over dj ratio, because the di over dj times 1 over di is dj, which in the end, it's very easy rule. If I already picked j, then move to the new location with minimum of 1 and di over dj. And this is something, maybe again, we have just discovered something that you might have seen in other contexts, like Metropolis algorithm. But so we have just discovered this rule that move to the new point of course, we cannot move with probability higher than 1, but minimum of 1 or the ratio or degrees, and otherwise stay in I. And again, we see that if my degree is much lower than the degree of the node I am going to visit, then I will want to stay in the node I am currently in longer to offset the imbalance in the original context. So here is the implementation of this, and as you can see from the implementation point, it is really a minor tweak in the code. I can use for loops, so I can easily implement it. Then there is only, maybe not only, but then one issue, that note that I ran this for now 1 billion times. 1 billion times, and it takes 1 minute, around 1 minute. So because the output doesn't show, I will not rerun it. But you might ask, why do I run it 100 times more? With normal walk, it was enough to do 10 million, and I got very nice results. If I am doing this corrected walk, actually I need to do many more steps to get convergence. And actually, in order to get a good convergence, we would need 10 billion. So it would run around for 10 minutes to get good convergence. And intuitively, what is the reason? The reason is that now for low degree nodes, first of all, I might be staying with them very long. If, for example, low degree node is connected to very high degree node, then I'm staying for many periods in this node. But on the other hand, intuitively, there is a higher risk because of this, that I will not visit some low degree node very fast. So in a sense, doing this corrected walk works, and we will check in a second that it works, but the convergence to the stationary distribution is much slower than in the uncorrected walk. And I ran it, and here is the information how many times I have visited a given node, and roughly we see that it is almost the same, but sometimes we have this extreme value very high, exactly because this walk has a much longer time that it takes it to get to stationary distribution. I can do a histogram of number of visits to a given node, and we see, okay, it is pretty well concentrated around the same value, but we have some nodes that are very rarely visited and some nodes that are much more frequently visited, and as I would expect. And this is something we didn't have in the original walk because of creation of those self loops that we have created. So let us analyze it a bit. So I put this data into a data frame. So this is another thing nice in Julia, that, you know, I was doing simulation, I was doing numerics, now I will do just data science. And, you know, you can all do this in one notebook without a problem. So now I create a data frame with those nodes. So what I put degrees of nodes and number of times I have visited a node. And first of all, I aggregate it. So we see indeed that here mean is around 26,500, the same median, but maximum is 2 times more and minimum is 0, which means in this walk, after 1 billion steps, there are nodes I have never visited. You know, as I said, if we do this 10 billion, with high probability, you will always visit someone, but 1 billion for this walk is not enough. And this is because we have this power law distribution of degrees. We have started, like half an hour ago, discussed this. So I have a power law distribution of degrees. So this corrected walk converges quite slowly. So I can aggregate it to get a mean and standard deviation of number of visits. And what we can notice that actually the biggest problem we have for low degree node. So maybe for the mean, it's not so bad. So if I aggregate the data by node degree, so average node of a given degree indeed has a number of visits as it should be expected. But what I see is that standard deviation is very high for low degree nodes and very low for high degree nodes. And for example, range of minimum and maximum, also we can see that actually I can get 0 only for degree 1 and 2. And those very high values are also only for degree 1 and 2. And as I increase degree, you know, it becomes much better concentrated. So the conclusion we learned from simulation probably also could be proven theoretically, that actually the highest variability in the number of visits will be for low degree nodes. So let us have a look at it. So if I look at mean number of visits by degree, indeed we can see that there is no trend here. Of course, this is very squashed on this side because we have just a few very heavy nodes, as we discussed. But the interesting thing is, if we look at standard deviation, that standard deviation, as promised, goes down as the degree increases. So what I wanted to show today are the following things. So at least I believe that it's nice to be able to do in one tool both stochastic and numerical simulation efficiently. So this graph was not so small. So it really, you know, if we didn't use efficient tool, it would be hard to do this analysis. But at the same time, at least I believe that those analytical solutions and computational arguments complement each other. So if you see one and the other thing, you can build quite well, I believe, the intuition for some standard algorithms that we have rediscovered today, like, you know, Metropolis algorithm or this power iteration method, which, like, of course, we had to guess it, but if, you know, for example, simulation gave us an idea what to do in numerical model, or from this symmetric argument, we knew how to design a simulation for the walk, for the solution. And what is important, that the tools that Przemysław showed you yesterday, and the Julia language, why do we use it? Because it allows us in a single tool to really scale computations if we need, but still you have nice things for plotting things, for aggregating data that I showed in the last part. And also I think the important thing that all this can be done interactively, so it's not a fully compiled language that you need to write a program and then run it, but rather you can interactively check what is going on. So if you would have now, we have one question regarding eigenvectors and eigenvalues, but I think I will either turn off streaming or will open terminal because in terminal I'm sure everything will work. And if you have any questions either regarding Julia or maybe regarding those walks, but I wanted to choose a topic that is probably well known so that you can have an easy mapping of theory that you know to code that I have shown, then I am open for a discussion. So thank you very much. And if you have any questions.